welcome to channel Edu9. Now we are going to discuss about the topic of subgroup. What is subgroup? Suppose G is a group with respect to a binary composition not and H be a non-empty subset of the group G, then if the subset H forms a group with respect to the same binary composition not, then H will be said to be the subgroup of the group G. For example, suppose we consider a group Z plus, because we know that the set of all integers forms a group with respect to the usual addition, which is the binary composition. Hence, any subset like 2Z, 3Z, 4Z, all are the subsets of non-empty subsets of the set Z, where 2Z is the collection of all even numbers, that is the multiples of 2, and 3Z is the collection of all whole integers whose are the multiples of 3. Similarly, all the sets, all the set 2Z forms a group with respect to the same binary composition plus. Similarly, 3Z also forms a group with respect to the addition or plus. That means 2Z, 3Z all are forming groups with respect to the same binary composition plus, for which the set Z forms a group. This implies that 2Z, 3Z is a subgroup of Z plus. We have studied the concept of subgroup. Now we are going to derive a necessary and sufficient condition for which a subset, a non-empty subset of a group forms a subgroup of that particular group. So here we have considered that G not be a group and a non-empty subset H of G forms a subgroup if and only if these two conditions holds. If and only if means necessary and sufficient condition, that is both the implications, both implicative statement. That is, if H naught is a subgroup, then these two results holds, and also if these two results holds, then H will be a subgroup of G. First of all, we considered that H naught be a subgroup of G naught. Since H naught is a subgroup, then the properties of group, that is closure, associativity, identity and inverse, all holds in H. And you can see that these two statements are, one is closure property, another is inverse element property. So since H is a subgroup of G, then H itself is a group. Since H is a group, therefore 1 and 2 holds by the definition of group. And now our target is to prove that H is not a subgroup. Conversely, let the condition hold. That is, the condition number 1 and the condition number 2 holds. That means closure property and inverse element property are given to us. Then we have to establish two properties. One is associativity and another is identity element property. So let's move on. Since 1 holds, H is closed under not, this by default. Second, H is a non-empty subset of G, and we know that associativity and commutativity both are hereditary property. So since associativity is a hereditary property and H is a subset of the group G, therefore not is associative on G due to the property of group, not will also be associative on the subset H of the group G, therefore not is associative on H also. And now inverse element property. So 3 properties completed, and our next target is to find out the identity element in the set H. For that we considered an element A in H. By the condition 2, we know that if there exists an element A in H, then its inverse is also in H. Now, by the condition, we can state that if A is in H, A inverse is in H, therefore their composition must be in H. So A naught A inverse belongs to H, and we all know that A naught A inverse equal to E, that means the identity element. So A naught A inverse belongs to H means E belongs to H, where E is the identity element, hence H naught is a group, H naught is a subgroup of G naught is well established. The previous theorem was a necessary and sufficient condition for forming a subgroup for a subset of a group. Now we are going to discuss another necessary and sufficient condition to prove a subgroup. And difference between them, first of all we studied the statement. Let G naught be a group. G naught is a given group and a non-empty subset H of G forms a subgroup of G naught if and only one condition. What is that? A and B, two elements in H, implies A naught B inverse belongs to H. So the difference between the previous theorem and this theorem is there was two statements to prove a subgroup, and here is only one statement. When we are performing any particular problem, then it is easier to us to prove a subgroup because there is only one condition to establish. So let's see. First of all, we considered that H naught is a subgroup of G naught. Then H naught is also a group, and we consider two elements A and B from H. Since H is a group, therefore there must exist four properties: closure, associativity, identity, and inverse. Since inverse of each element is in that particular group H, so we must have B belongs to H implies B inverse is also in H. So from that we have implied that A B inverse belongs to H, and we know that the closure property always holds in a group. So from that we can conclude that A naught B inverse is also belongs to H. So this is our first part, and in the second part, conversely, let the condition hold. That means A and B, two elements in H, then this result holds, that is A naught B inverse belongs to H. From that we have to establish that H is a subgroup of G. That means we have to establish four results: closure, associativity, identity, and inverse in the set H. First of all, we consider a particular element A is arbitrary element in H, and we perform it like A B belongs to H implies A itself only a single element A is in H. Then we can perform that A naught A inverse belongs to H from this condition, because for any two elements A and B is in H implies A naught B inverse in H. If we consider that we are not going to consider two elements, we are going to consider only one element, then A is performing the course of A and B also. Therefore A naught A inverse belongs to H, and we all know that A naught A inverse, that is the composition of an element and its inverse element, must implies an identity element. So A naught A inverse belongs to H implies E belongs to H, where E is the identity element. So identity element property is solved. Next, E and A both belongs to H, because we have already proved that identity element is in H and A is considered is in H. So A belongs to H implies from the condition that E naught A inverse is also H. Here A is performing the job of B and E is performing the job of A. Therefore E naught A inverse belongs to H, and we know that if we compute any element with the identity, then it returns the same particular element. So E naught A inverse means A inverse which is in H. So that implies the establishment of inverse element property. And now we know that associativity is the hereditary property. So H is a subset of G implies, since naught is associative on the group G, therefore naught is also associative on the subset H of G. Thus associativity also is established last property. Now only one property remained, that is the closure property. For that we consider two elements A and B in H. We have already established the inverse element property. From that we can say that the inverse of B must be in H. Therefore A and B inverse both are in H. From that, using this condition, we can say that A naught B inverse belongs to H, and B inverse means ultimately B. From that we can conclude A naught B belongs to H. So it is clear that the four properties are satisfied, hence H naught is a group. Since H is a non-empty subset of G, therefore H naught is a subgroup of the group G naught.